Welcome to the next video in the group theory series. In this video, we introduce product tables, which is a way of displaying what any given group is. You can see here the plan for the video. Okay. We begin with an example. To the left, you can see the product table for D6. That is to say, the symmetry is of a triangle. It has a row and column for each element. So let's gesture over here and see R squared, S, RS, R squared, S. That's every element of the group. Also, likewise for the columns, 1, R squared, S. I guess, yeah, it runs a little off the page, but S, RS, and R squared, S. Consider, for instance, the row labeled RS and the column labeled R squared. So let's find the row labeled RS and the column labeled R squared, which seems to have this value. Let's see why the value at their intersection is R squared S. And we're going to compute this RS R squared. Notice RS on the left for that corresponds to the row, and R squared on the right, that corresponds to the column. So we start computing this product, and we do what we've seen in at least one other video, which is if this is an R squared, I split it into an R times an R, and I move one of those R's to the other side of S. I have to take its inverse when I do so. I do it one more time to get this R squared. These two R and R squareds cancel, left with this, and then that R inverse turns into R to the n minus 1. Here, n is 3. And that's why R squared S is located at that coordinate of the table. So what's entered at row RS and column R squared is the result of the product, RS on the left, R squared on the right. The viewer is encouraged to confirm the rest of the content of this table. Let's look at another example. The Z3 table, you can see it over here. So 0 plus 0, this is the additive group for Z mod 3. 0 plus 0 is 0, 1, 2. In fact, if you always start by labeling the identity element as the first element of each row label and each column label, then this first row will always just be a listing of the group elements in the order that you list them up here. And likewise for the column here, it will just correspond to these elements because you're just combining them with the identity, and so they just stay what they are. That's what the identity does when it combines with other elements. Anyway, right here you have 1 plus 1 is 2, and so on. Now, I want to, sort of sell the whole idea of a table by arguing that it's a little bit useful for something. So, by the way, of course, Z3 is additive, so it makes it a little awkward to be calling this a product table, but oh well. So anyway, one nice thing about product tables is that it can sometimes show you when two groups are basically the same. Compare the Z3 table with the subtable of D6, so you may have to come back up here to see this subtable of D6 corresponding only to the elements of rotations right here in this sort of 3 by 3 subgrid. Now here I've overlaid the two tables, okay? So this is the subtable of rotations only. So where I've superimposed the two tables, they're basically the same table, right? So 0 increments to 1 increments to 2. Well, here we had 1 to R squared, very similar, right? Same thing down the other axis. When you put 1 and 1 together, you get 2, and also in the dihedral group, when you put R and R together, you get R squared. So there's a very, very almost one-to-one correspondence between the two. So it will make that formal more later, but anyway. The idea here is that the only real difference between Z mod 3 and this subgroup of rotations is the names that we're giving to the elements, right? If you just switch the name 0 over to the name 1, switch 1 over to R, switch 2 over to R squared, you switch the names, but the interactions that are shown in the table are exactly the same kinds of interactions, right? By relabeling things, you don't have to change anything's position in the table. So that's one neat thing that a table can show you. Uh, the interested viewer is invited to see for themselves that no such thing, no thing like that happens if you draw the table for Z4, right? You might think, well, it's just that they both had three elements, right? Z mod 3 has three elements, and D3, or sorry, D6, the subgroup of rotations also has only three elements. Well, maybe that always happens when you have two groups that have the same number of elements. No, in fact, it does not happen. And you can see it by drawing out the table for Z mod 4 and the table for Z mod 2 cross Z mod 2. And you'll see that, in fact, you don't get any such thing in their tables. When you try to superimpose them and see one as a relabeling of the other, it just doesn't work no matter how you do the relabeling. Okay, there is a little intro to product tables. Now we're going to make a claim and give a proof. I claim that every row of a product table contains every element of the group, and likewise for the columns. I'll only prove this for the rows, since the proof for the columns is spiritually identical to that for the rows. If we fix an arbitrary row of the table corresponding to little g and big G, and an arbitrary element little h in big G, then we find, right, that what we are trying to find is a column of the table corresponding to an element x in G, such that h is at row G column x. And to find such an element is to find a solution to gx equals h, because that's just the equation that defines what you're going to find at row G and column H, right? So if we're trying to find the column X, which has H in that column and G is the row, then this equation is what we would like to solve to find the column. By an earlier theorem, this always has a solution for X, and therefore this column exists. So what we have effectively shown is that on row G, no matter which H you pick, you'll always find a column with that H in it. Oh, actually, I see that in the notes, I also stated and proved something that I skipped over in my little sort of lecture notes, which is that commutative groups always have symmetric tables. And so here, let's just talk through the proof right here. The fundamental idea is going to really just sort of lean on what do we mean by a symmetric table, and the meaning of a symmetric table generally, even when it doesn't have like index numbers. We could impose index numbers, but that shouldn't be that necessary. So if you just stick with group element labels on the rows and columns, then what it means for a table to be symmetric is that the element located at row G column H is the same element as what you find at row H column G, right? By transposing the order of row and column, what you find in those two coordinates is always the same thing. That's what it is for a table to be symmetric. And in fact, that, just by definition of the table as storing GH in the row G column H coordinate and storing HG in the row H column G coordinate, if the group is commutative, then those will be equal, and therefore the coordinates of the table at those two coordinates will always be equal. Okay, let's move on to just a slide. So let's move on to a slightly frivolous thing, although it'll, be a little useful at some points. And it is this little software toy, right? So I just kind of want to show off one of my toys. Uh, it's a small program in Python that I wrote to help compute product tables. You can see the source code to the left, but the basic idea about how to use it is shown where I make the table for D8. I'll scan through some of this in case anybody wants to see some of the code. But, right, so you define a class with some methods, helper functions for various things, little printing method. Most of the work, most of the interesting stuff is in this add rule method, which calls on other helper methods anyway. But you can see how I use it here. So I basically just make up a string with all the names of the elements in D8, comma separated, and I use the commas to split it all up, get a list of all the names of all the elements. That's all just so that I can initialize my product table. I also kind of, then sort of spill it all out so that I can refer to all of these elements. But anyway, in these for loops, it's a bunch of like logic and calculations on the order in which the elements occur here and so on. But the basic idea is that I just kind of compute what each product should be and add that as a rule. And then down here, I go ahead and print out the table that it produces. You can see this relatively nice pandas data frame printout. But the sort of interesting thing is that it looks right. It looks like it has correctly populated the table in the same right, not exactly in the same way as the previous thing that I showed by hand because that was D6. This is D8. But in any case, it looks right. Now you might be wondering, right, okay, if all you do is you have to like figure out what the rule should be and then enter the rule, well then, how is that any better than just doing it by hand? It's not terribly much better than doing it by hand, but it does a couple things for you. For one thing, it checks consistency. So if you enter something into the table that conflicts with something somewhere else, it'll let you know, and it won't let you add that thing. And for another thing, when a row or column is missing only one thing, it'll fill in that row and column for you. Just a slight aid in entering things more quickly. In fact, besides just making and showing the product table, it'll also be helpful later on where it will be useful to have sort of software representations of large groups, which this uh, can in principle do. And that'll eventually help us to see how certain groups relate to each other. In particular, what I have in mind is that I'll be using this when I want to demonstrate certain homomorphisms. But anyway, that's for later.